Hi, my name is Bob Cheesebro, and I'm a technical consulting engineer in Intel's compiler team. Welcome to the sixth in a series of videos covering Intel compiler vectorization essentials. In this video, we will explore the topic of call site dependence in addition to the uniform and linear clauses in more detail. Here we have a function definition which is declared as a SIMD-enabled function, formerly known as an elemental function. The function receives an integer pointer and an index variable I. Then it prints the contents of the array. Since the array base index will be constant across all iterations, and the only thing changing is the array index in a linear fashion by a unit stride of run, we declare variable a as uniform. Value of a is broadcast to all iterations, and declare I as linear with unit stride. Also, we will assume that we are targeting the SSE architecture here, meaning 128-bit vector registers, and hence we specify the vector operand to have a SIMD-len of 4, which would be appropriate for a data type of int, which is a 32-bit data type, on a 128-bit vector width such as SSE or SSE2. Regarding the call site, here we see a for loop iterating from 0 to n-1, and for every iteration of the loop there is a call to foo function. In order to vectorize this loop, the compiler looks for a corresponding vector version of the loop. The checks in this case are: 1. Is there a SIMD-enabled version of this function? 2. Do the parameters passed from the call site match the clauses criteria on the callee site? Only when these two conditions are matching, as in the above case, the compiler generates a vector version of foo inside the loop. For more information, you might want to refer to this reference. In order to understand that the compiler does call site checking before it decides which generated vector function call will be used inside the loop, let's consider the differences between the top loop and the bottom loop in the middle text box here. The main difference between the two loops is the second argument to foo. In the top loop, the second argument to foo is the loop index I, so the compiler sees a linear access pattern for the second argument. In the bottom loop, the second argument to foo is a variable k, which gets its value from the contents of array b and will not in general be linear, monotonically increasing or decreasing values. So for the bottom loop, what the compiler sees at the call site is a nonlinear second argument usage. There is no OMP declare SIMD version of the function that covers the case of uniform first argument, second argument nonlinear. As seen from the above vectorization report, it is evident that the second loop's foo call is not a vector call. The usage at the call site does not match up with the OMP declare SIMD annotation that defined the function, and we see that the compiler's vectorizer states no suitable vector variant of function z3 foo pii is found. There is no matchup because the second argument is not linear. So though the developer has provided a vector-defined version of the function foo, the compiler was intelligent enough to identify that the vector version of the function is not applicable in this case because the call site implementation did not match the function definition's vector attributes. So the compiler defaulted to choose the scalar version of the function foo for the second loop. This is all due to the existence of the linear I:1 imposed in the second argument in the function definition of foo. In the previous slide, we saw a bit of a dilemma. We need the linear clause to be in place to help in cases where we invoke the function with its second argument as linear as in the first loop. But the presence of the linear clause is preventing us from vectorizing the second loop. So we avert the dilemma by using multiple vector annotations for the function definition. In the previous slide, we saw that the second loop introduced wasn't vectorizing because the function foo, called inside the loop body, did not have a vector version that matched the second argument criteria passed from the call site. The problem is due to the existence of the linear I:1 clause. What we see in this slide is that the developer has now created multiple flavors of the SIMD function to handle both call site invocations. The first loop continues to vectorize just as it did before because it takes advantage of the linear access pattern identified at the call site. The developer has provided a declare SIMD clause covering this use scenario. For the second loop, the compiler will do some checking. Here, using the declare SIMD clause, the developer has explicitly stated that there should be at least two vector versions of the function, one with the linear clause and another without the linear clause. Now when the compiler attempts to vectorize the second loop at the call site, it sees a pattern for the call site of foo whereby the second argument is nonlinear and the first argument could be uniform. So it can check to see if it has a vector annotated version of the function foo that matches this usage pattern, and it finds one. Now the developer has provided such a vector definition of the function foo, which doesn't have a restriction on the second argument being linear with unit stride. This fits the pattern the compiler identifies in the call site for the second loop, so the compiler can now vectorize that second loop. Here is a list of restrictions using SIMD-enabled functions.
I won't read each of these, as it is best to consult the documentation for more details.
But the general idea is the following. The function must be a structured block, no gotos, one entry and one exit per function. Arguments can be included in one linear or one uniform clause only. You can't declare variable x to be both uniform and linear, for example. Do not nest OpenMP threaded code inside the function. Do not use long jumps or set jumps. That's the rough summary.
This concludes our 6th video. Please take a few minutes to watch our next video in this series, Performance Essentials 7, where we will explore how to measure your vectorization success.
Here are our requisite optimization notices and legal disclaimers.